Okay, so this is the exam I gave. Wow, so much forever. Pre-pandemic. This is a before society class. And again, the obviously I'll give you something different, but this is kind of the more or less the format that I told you that.
You sure you don't want to do something very similar?
You know, toward the end of the semester, that gets a lot more tempting. You know, that's.
I mean, even like right now.
Toward the end of the semester, that gets really, really tempting. Okay, so we will just the homework. Maybe I may depends on how far I get today. I may put off the homework until Tuesday. I probably will because I want to do a little bit more with cross products. So that's the last thing to do on cross products. Okay. So I'll just keep on putting it off. Maybe it'll be due April. You know, maybe August.
August.
Okay. Maybe we'll do the same with the test. Yeah. Okay. So we looked at the infinite plane. Okay. Which is like it's really big, like this. It's very, very okay. Well, we looked at the infinite plane like this. And what do we do with it?
Put charge over.
Yeah, we put charge in the charges. Uniform. So this is uniformly charged.
Is it a flat?
Yes. And so the kind of the side view is this. And so we decide what this is. Here's my plane. It'd be like this, but make this plane infinite, then put charge all over the place. That's what we said. Okay. But do we want to find the electric field here? We found out something odd. What did we find out about the electric field there?
It's perpendicular to the plane, all of it.
Okay, so it's perpendicular. So it's like this. It's down like this.
It's a constant.
Yeah. It ends up being a constant there. Remember what it is?
Sigma over 2 epsilon.
Sigma over 2 epsilon naught. Suppose you had suppose somebody were to write this as A pi sigma times 2. Is that right?
Yeah, because it's 4 pi.
Yeah. If somebody writes it like this, what have they done?
They just substituted sigma with
Yeah, just multiply the top and bottom by 2 pi. 4 pi epsilon naught is K. So this is your K, your pi. So I'm always going to write this, but just so you know, if you come across a book or someplace that writes it like this, that's all they've done here. Does that make sense?
Yeah. Yep.
Okay. So let's take the following case, and I set this up on Wednesday. This one is sufficient. So I'm going to take 2 sheets like this. These are 2 sheets. I'm going to put a battery here. Don't confuse this with bad tree.
Because it looks kind of similar.
It looks the same. You know, bad tree would be like Wizard of Oz thing like this. It's evil. That throws apples at Dorothy. That's bad tree. Good to know. You never know when you're going to come across one. Okay, so what do we do with our bad tree? Okay, we put a wire on it, and I'm going to draw a wire like thick wire. You had this picture last time. So this is the wire. I've drawn it thick so you can see what's going on here. I think this marker is already as well.
see the teeth on that.
I'm not messing with that. Okay, so we have this. From now on, when you have a battery, what do you think of a battery as being? It's a source of
Electrical.
an electric field. So the fact that this is positive here means that the electric field is going to be set up like this here. And then it's going to be set up like this here. Okay. Now, what did we say that electric field is going to do? If you're a little electron here, and if you see this electric field moving this way, what happens to you?
Pushing you to the battery.
Yeah, you're going to have a force on you, and that force is going to take this electron all the way over here. It gets kicked over here, and then the electron is out here. Through chemistry, that electron by a chemical reaction gets kicked over to here. I think the chemical reaction makes this incomprehensible to me. It gets on this side here, but once the electron is on this side, what happens?
It goes to the second outlet.
Yeah, it continues to go here, and then the electron is now transported to this side. Well, this is going to keep on happening. All these electrons here are going to be basically brought over here like this. You all get deposited here. What's going to happen? This sheet is going to be left
With positive charge.
positive charge.
What's the switch you said?
What?
You said like something flips or switches, like what goes?
Well, the electron, just chemically, this electron gets switched over here. Okay. And then it ends up here. And then this, it acquires a negative charge. What do you know about the charge on each of these plates? How does this charge here compare to that charge here?
They equal in value, but opposite.
Yeah, so this is a plus Q, then this will be a minus Q, or if this is a plus sigma, this is the minus sigma, because you're assuming the plates are identical. Okay? Does that make sense?
Yeah.
So let's actually see what we have here. Oh, when you say you have a dead battery, what does it mean to have a dead battery?
Doesn't react anymore to switch the electrons from one place to another.
Yeah, the electron is no longer, the battery can no longer take the electron to here to here. And that's when you say you have a dead battery. Okay, so let's look at the field here. So I can draw a side view of this. So here's this part here. Plus sigma, minus sigma. And let's draw the field. Let's draw the field here, here, and here. Okay. So what's the electric field look like over here?
Charge going outwards to the negative.
Okay, so let's add them together. Yeah. So how's the electric field look here due to our positive plate?
Goes perpendicular in both directions.
Okay, so just right here, then it looks,
At the point. It goes
has to be going this way. So this is E due to the plus charge. What is that given by? It's given by sigma over 2 epsilon naught. Now, what's the electric field look like here due to the negative plate?
It's the opposite direction, but
Was it, but since it's out of farther distance?
Does the distance matter?
no, it's constant.
Because it's the infinite plate.
Oh,
Okay. So what happens from this plate here, the electric field at this spot due to a negative plate is like this. And this is going to be minus sigma over 2 epsilon naught. So out here, what's the electric field?
Zero.
There will be no electric, so the total electric field out here is going to be 0. Now, what about over here on this side?
Same thing.
Now, let's go through and do it. So how's the electric field look here due to our positive plate? Let's be going this way. This is our sigma over 2 epsilon naught. And how's the electric field up here due to our negative plate?
To the left.
That's what we're going to go. So what happens here, again, these cancel because they're equal and opposite. So your total electric field is 0 here. Now, let's look in between here. How's the electric field up here due to our positive plate?
To the right.
That's what's going this way. How's the electric field up here due to our negative plate?
Same direction.
Has to be in the same direction. This one here is E minus. It has to be sigma over 2 epsilon naught. Why isn't it negative? It's going to the right. How have I counted for the negative sign here?
You would subtract 1.
From the picture. How have I counted for the minus sign here? By having the arrow going this way here. That's how I've accounted for the negative sign here. Okay. So it means that the total electric field here in the center is the sum of these two guys. Okay, so you just get sigma over epsilon naught. And how would it look? It would look just like this. So this is the electric field. Okay, so what is special about that electric field inside there? It is
Constant.
Yeah, constant. This is the constant E field. So if you're in a lab, if you need a constant electric field, how would you make a constant electric field?
Like that.
Yeah, you basically go to a kitchen, pull out 2 cookie trays. So you pull out 2 cookie trays like this. You hook a battery between the two, and in between, you wouldn't go toward the edges because you'd start getting red edge effects. But if you're in the kind of the center region here, you're going to have a constant electric field. Okay, does that make sense?
Yeah.
So from a laboratory point of view, this is really, really important. This is actually how you make it constant electric field. Okay. And that'll be the main result we use for this. Okay, later on, meaning very soon, we're going to find out what this device is called. This device is called a capacitor. Okay, so this right here, this is going to be a capacitor. So a capacitor is going to be a device that basically stores electric charge, and also it basically stores an electric field inside here. But we don't know that yet. Let me give you kind of the.
Thanks for telling us that we don't know.
Yeah, that's crazy. Okay. Well, let me show you how you're going to write this here. This is too cumbersome to keep on writing it like this as you draw a capacitor. So the symbol for a capacitor is going to be this. It's going to be 2 parallel lines.
Makes sense.
This will be the symbol.
Every single one of those would have to have a battery, right?
Correct. Now this right here, this type of battery here, this is called a DC battery. DC stands for direct. It's current. Don't confuse it with the Marvel batteries because they're incompatible. Okay, they're entirely different. Okay. So what does it mean to be direct current?
So if you had alternating current,
It goes one direction.
inside the.
Yeah, exactly. We'll see how to make that. It's actually true. So in this case here, it just means that basically, if you look at how the charge flows, the charge is only going to flow in one direction. That's what it means to be direct current. Now, we don't want to keep on drawing this for the battery here like this. So we're going to have a symbol for this guy. So the symbol for this guy is the positive side, we make a big line like this. And then the negative side, we make a little sign like that. Okay. So this is the positive part, and that's the negative part. And this will be the symbol for a DC battery. Yeah. And wire, I'm not going to keep on drawing thick wire like this. Instead, what you're just going to do is have a line.
Okay.
So just use a line.
Dr. Lux.
Let me hang on. Huh? Yes, Vasily.
But if we write a symbol for a capacitor, we don't have to write this separate symbol for a battery. It's implied. Okay.
No. You have the different things, and then you start making circuits with them.
Okay.
So this circuit here, if I were to draw that just in terms of basically symbols, what does it become?
Exactly what's down there.
So I have the battery here. I'm sorry, the capacitor here. Battery here.
Hooked up.
And then I go like this.
Oh, okay.
So this picture here is really this picture. Okay. We'll be doing a lot more with that later on, but right now, this is just, don't worry about this quite yet. We're going to hit this really hard. Not really.
Capacitors are crazy. The ones in the microwaves, when you're taking them apart.
But you want to be careful with the capacitor.
Yeah.
You can actually get.
It is a lot of.
You can actually get hurt actually really bad if you don't hold your own capacitor. I'll show you what to do. You don't want to necessarily take and go. No, Never lick your electronic instrument. Anything electronic, do not lick. No, nothing good is going to happen with that. Okay, especially with this guy. Questions to that?
Want to hear a short story about licking the electronic devices?
Do I regret saying yes?
No.
Okay.
So in Soviet Union, there was a thing that how to get like kind of electric high a little bit. It was messed up. People would take like big batteries, put spoons to them, like wire them up, and put spoons like in your mouth, and they would like shock you. And it was like a terrible thing to do. And
Yes, I agree.
and it's just common knowledge, so you know what Soviet Union kids did.
Good to know.
Yeah.
Okay, so that's one activity we won't do. Okay. Yeah, we'll come up with another lab. Okay, I'll get rid of the lab we were going to do on Wednesday.
We can kind of get back to the Soviet Union like that.
It worked, or they just get seriously injured.
I mean, it usually older kids would like mess with younger kids like that. So it wasn't even like to get high. It just
Shit,
like,
Johnny died.
It's going to be too much. Okay, so I want to talk about an application. Let's talk about an application. Let's ask what happens when you place an electric dipole and an electric. What did we say electric dipole is again?
Two negative and two positive charges.
Yeah, you have a positive charge and negative charge like this. So if I say that this is my, and what symbol do we use for dipoles? P. So if I say this is P, which end is positive, which end is negative?
arrow ends is negative.
So this is positive,
I guess the other one.
okay? The magnitude of this is, how do you define the magnitude of a dipole? Let's call this plus Q. We call this minus Q. The distance between the two is D. The magnitude of this is,
DQ.
yes, Q times D. Okay, that's the magnitude of this. And by definition, the direction goes from negative to positive. Again, when you're dealing with the chemists, often the chemists draw these. They don't do this because they're more looking at the electric field, and the electric field would go which way?
The other way.
The other way like that. So sometimes when you look at the chemists, they're doing something weird. They're really not, because it's useful for them, but I'm still going to make fun of them. But the P actually goes the other way. But sometimes just because they're going to use that in a way that's convenient for them, you're going to draw it the other way. Okay, that makes sense. So what we're going to do, we're going to take this and we're going to put it into an electric field. I'm going to assume for simplicity that the electric field is a constant. So here's our E. And here's our Q.
Was the whole dipole being moved?
We're going to find that out. Can't wait to find out what's going to happen. So what would happen?
Oh, you're right.
What would happen to my little dipole?
Let's try to draw a picture of forces on it.
Yes, draw the forces on it. What would be the force on this guy?
Orthogonal projection of Lie field on the dipole. Sorry. Is it kind of scary?
I would just kind of say it's something very simple.
Right.
Yes, done. Okay. This is positive. That force is going to be like this. This will be the force on positive. And it'll go like that. How come? How are the force and E and Q all connected?
They have the same direction.
Yeah, your E is your F over Q. So the direction of this is the direction of that. That makes sense? Okay. So that's going that way. What about our little negative trend? Yeah, that's going to be going this way here. Okay. So if you're a little dipole here, sounds like some kid song, isn't it? I'm a little dipole, short and
Yeah.
sweet. Here is my plus sign. Here is my feet. I don't know. So let's say you have this guy here. So what would happen with this?
Spin.
You're pulling this way, this way. You're pulling this way, this way. What's the net force on this guy?
0.
Actually, it was, it would just
So it's gonna
go
go
like that.
like that.
But then
It's gonna try to orient it like that.
moment of.
Yeah, it would just-
Okay. So what I want to convince you of is that the there is a torque.
It-
Hang on. Okay. There is a torque on the dipole. Well, let's say the electric field. The E exerts a torque on the dipole given by. Okay, what's that torque given by? It's not one but obvious. The torque tau is given by P cross V. I'm going to draw that. Okay. So there's going to be a torque in this guy given by P cross V, and the dipole aligns with E. Okay. So you do this here, and again, that one you can just the aligning part is easy to see because that force is going this way, that force is going that way. That's going to align all of this. Okay. The torque part isn't quite obvious. Okay. So what I want to do is I want to have a little review on cross products because we did them last semester, but I think it's one of those things that are weird enough that I want to go over them more. So I'm going to go over some cross product stuff and then talk about how to do this here. Yep. Well, it's just the true, not the true matrix. It's
Well,
just-
but,
okay.
well, you-
They're different. Okay. Yep, so let's do a little review of cross products. So before we derive this equation, let's review cross products.
That makes sense. That's how my base works. And it's why it's like-
Okay, so how do we define cross products? Here's A. And here's B. What can I always do with vectors?
Components.
I can break them up into components. So I'm going to take A and I'm going to break it up into what components?
A, B, sine, theta.
Hmm,
A parallel line.
yeah, a part parallel to B and a part perpendicular to B. So how do I do that? I go here and what do I draw? I draw my little perpendicular like that. So this part right here, I call that A parallel. So that's a component of A parallel to B. Okay. And this part right here, this is, I'll call this A perpendicular, and this is the component of A perpendicular to B. Oh, did that go off? Oh, also, as long as I'm on here, one of our, there's a classmate here who is going to be out of commission for probably quite some time. Can I get one of you who takes good notes to legible notes, meaning to actually photocopy them and send them to me so I can send them to the student because he's going to be out of commission probably for a while. Okay, just if you come see me after class, and I'll send them to him.
Legible notes, you said?
Yes.
Oh,
Okay. So some people that means please don't because I'll just leave it at that.
okay.
Okay. So how do we then define the cross product? Okay, so how do we define the dot product?
It's the component. Oh, it's no.
So if I have A dot B,
A, B, cosine.
yeah, that's your A parallel times the magnitude of B. And then if this is theta, that's theta, then what is A parallel? Yeah, this is going to be A parallel, is going to be your magnitude of A cosine of theta. And that gives me this. But you never see it written like that. You really see it as A, B. cosine of theta. Okay. But what it is a parallel component of one vector along the other. That's fundamentally what it is. When you do these things, these are always scalars. So when you do a dot product, what you better not end up with in your answer? You better not have your IJs and Ks in there. If you do, that's fundamentally wrong. I know there's some mathematicians, if you in top 3, if you left IJs and Ks in your dot products, it didn't go well. So just don't do that. All right, so that's a dot product. A cross product, we're going to basically define similar to this. So first of all, this is going to be a vector. So I'm going to draw the magnitudes over here. And what do you think this is going to be then?
Yeah.
Okay, so it's going to be the perpendicular component of A
It's there.
times the magnitude of B.
Orthogonal component.
That's all. How much of your A here is perpendicular to B like this? What's your A perpendicular? Yeah, this is magnitude of A,
Sine theta.
sine of theta. So we're going to take that, put it in here. No one ever writes it like that. Instead, what you do, you write it like this. But again, what it is, it's really this. Just like this one here is really, really bad. Kind of keep that mental picture in your mind. Does that make sense?
Yeah.
So the question is, how do we work these out? So first of all, let's do the direction of it. With the right-hand rule, and then we'll talk about actually calculating one.
It should be perpendicular to both of them.
Correct, by definition. So how do we determine? The direction of the cross product. And so from first semester physics, what do you use? The right-hand rule. And why do we call it the right-hand rule? We're going to use right hand. This is one of the few times in life where a lefty has an advantage. Remember why?
On test.
If you're a lefty, your hand's occupied, this hand is free, you won't be making a mistake. If you're right-handed, it's very easy to do what? You're on a test. Your right hand is occupied, your left hand is free, and you're going to be using your left hand without thinking about it, and you're going to have everything done. Okay? So lefties rejoice. That's one of the few times you get an advantage. Okay. So we use the right-hand rule. So let's remember how this goes.
I don't think he likes this class anymore.
Well, that's just for him. Because I don't have to grade Ralph's first test. I think he did really bad on it. Okay, so that's the. So let's look at this guy here. Okay, cross B. Okay, so how does right-hand rule? Let's see if you remember what to do. Take your fingers. Where do they go?
B. No,
Take
A,
it.
A,
Okay.
and cross them
Yeah.
with your hand.
Take your fingers, these fingers here, and cross them in the direction of A. So if A is going this way, what way could my fingers go? Any orientation. If I go like this and I rotate my hands, it doesn't matter. My fingers are pointing along the direction of A.
Okay.
Now, what fixes the direction of your hand?
Direction of B.
Yeah, you have to bend them in the direction of B such that your hand doesn't hurt. So let's make our hands hurt. Let's do it wrong. A, cross into B, ow, 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 ow. No, stop. Okay. A, ow, 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 stop. So I have to do A, I'll rotate my hand like that, then I can bend them easily into B. So A, cross into B. Then where's the result? The result is into the board. So if I call this C. You have A, cross into B, C is into the board. How do I denote something going into the board? X, and then you put that little circle. That's your C. This means into B. When you do a cross product, what do you know about the result of a cross product? It must be by definition perpendicular
To both of the vectors.
to both A and B. So this must be perpendicular to both. A and B. Okay, let's try another one. When you get to magnetic fields are one gigantic cross product. there's just cross products everywhere with magnetic fields. That's the whole basis for it. Okay, let's try this one. Let's say this is A. Let's say this is B. I want you to find. What does that one do? Up, down, right, left, in, out.
What did you say?
Up, down, right, left, in, out.
Down,
It's.
I'm hearing down,
right,
down, right,
That way, left.
left.
Left, no, it's not.
that's right.
No, it's right. I'm just reiterating what people were saying.
Well, left if I'm turned around.
Right
It's like
down.
at 5 o'clock.
Right.
5.
Why my thumb is
Right
pointing?
down.
Right.
That way.
Okay, where do your fingers go first?
A.
Go along the direction of A. So I have to go like this. Well, any orientation like this will work. Then what do I have to do?
In.
Fold in.
I have to bend them in the direction of B. How is B going?
Into the
Into the
board.
board. So if I do A, crossed into B, because B's in, so A, crossed into B, my thumb's like this.
So nice to have 1, 2, 3. and
So what do we know about this? This is perpendicular to both B
and A.
and then A. Suppose instead I had this.
It would be that, but negative.
It would be the other way.
Does everyone agree? So you have B crossed into A, this guy here. That would be B crossed. A. Yeah. Okay, that makes sense? Let's try another one. So let's say I have A. And let's see. What's that one?
Upward.
Just cross B. Everyone agree? A, cross and B, that's not. Okay.
Oh, we can send this for a whole test.
Well,
This is our whole test.
that's all we're gonna do. What about this guy?
You should take out 3, should have.
Hmm?
That's basically.
No,
What?
he only took.
You took out 3, that's pretty much.
No, it's, I know, we did this last month.
Plus,
Into the board.
We have into the board.
Go down.
A, cross B, that's into the board.
Flip it.
Suppose it had B crossed A.
outside the board.
Out.
That would be out of the, how do I denote something out of the board?
A dot.
Yes, again, if we do this guy here, I call this vector D. If I do this guy, this is B, this is A. Where do your fingers go first?
B.
Along the direction of B, and then what do we do? We bend them into the smaller angle going to A here. So B crosses A, my thumb's coming out. So I denote that with a dot.
Who made up this kind of rule?
Right,
Really?
It's right hand rule.
last name was Hand.
Oh,
You had a rule.
And then they made it blank.
Crazy. Okay, I don't know. Okay, what's the dumb way to remember that this is in and this is out?
like an arrow.
Think of an arrow. If you see an arrow go away from you, what do you see?
This is makes 290
The
degrees.
cross product's going like, the cross feathers going like this. Arrow coming at you.
You're screwed.
Yeah, you're screwed because that thing's coming out at you like that.
Oh, that makes a lot of sense. Since
What's
it's a
the
90-degree angle.
Yep.
People would have it.
Does that make sense? Okay, we're gonna be all magnetic fields when we get to them. Everything in magnetic fields are cross products. We have right hand rules and we're gonna have a zillion right hand rules and a zillion cross products and everything else. So let's actually
Look at the white one.
let's do an example here.
The dipole?
Oh, yeah. Let's say I have A equals 2I plus 3. Let's say I have B equaling 3I minus 4A.
Negative 8i. Nope, nope.
And I want to figure out what this is. So Valentine's Day is coming up. You can't find chocolate for your hot date. So instead of you bring your date, 2 vectors and you're going to cross them. That says love. Okay. Okay. What does that equal?
It's hard to do our annotation.
2, 3, 0, 3, 0.
So we have A cross B.
Yikes, okay.
Let's just put them in here. So A is my friend 2I plus 3J. And we're going to cross that into my friend B. What is B? B is my friend 3I hat. I'm going to show you a really quick way of doing this in a little bit. Not quite yet. So if I just say you work that out, what would you do?
Construct the determinant.
No, we don't know that. You just multiply everything out. Right, you do this cross into this cross into this cross into this, plus this cross into this. You just use FOIL on it. Okay, did this so use the word FOIL?
Yeah.
Okay, so this crossed into this. Okay, the 2 and the 3 are just numbers. So 2 times 3, I'll write it like this. So this 2 times 3. And what is actually getting crossed? The cross product works on the vector part. The vector part is this I and then this I here. So this is I
It
cross
totally
I.
doesn't look like that.
Plus. Okay, now we have this crossed into this. So this would be 2 times minus 4. Then we have I hat crossed into K hat. Okay, what do you mean by next term? This cross this. So it'd be 3 times 3. J cross I. And plus, finish up for me. 3 times minus 4. J cross K. Okay. So what do we have to work out?
Just the cross products.
You have to work out all those little cross products. So I'll show you how to do it, then I'm going to show you an easy way to do it. Okay, so let's work out this guy. I cross. So let's work out the magnitude here. What's the magnitude of a cross product?
It's magnitude of A, magnitude of B, sine,
Magnitude of the first, magnitude of the second times the sine of
the angle between them.
the angle between the two. What angle does I make with I?
0,
Zero.
so 0.
0.
Sine 0 is 0.
What is the sine of 0?
0.
0. So this guy here is 0. Now that makes sense. What does the cross product tell you? It tells you how much of one vector is
Perpendicular.
perpendicular to another vector. If you have 2 vectors parallel to each other, there can't be anything perpendicular. Okay, let's work out my buddy here. What's my buddy I cross K?
Should be J.
Magnitude,
Oh, magnitude 1.
magnitude of I, magnitude of K. What angle does I make with K?
1. Oh, 90.
Sine of 90. 1, 1, 1, which is 4. Which is
1.
okay. Now, what direction is that going? That's
J.
where we're looking out. Okay, I hat goes on what axis?
X.
X. Right, and that's really coming out at you like this. That's I hat. K hat is,
Z.
so work that out. So this is really, well, this is really K hat. Then cross and I hat. That picture here is really this guy here. So work out, I cross K for me.
To the
I
to the right.
cross K.
Oh, it's coming out.
Like that.
Oh.
Okay. So it's going in that direction, but it has a length of 1. Do we have another name for that?
Negative J.
Yeah, this is really going to be minus J. Okay. Now there's a dumb way to remember. Let me show you another one. I think I'm going to show you the dumb way to kind of remember this. What about if you had J cross K? Actually, let's do another one here. Let's do the J cross. Yeah, okay, we'll do J cross K. So this guy here is minus J. Tell me about my buddy here.
Again, magnitude of 1.
Okay, so if you look at the magnitude of this guy. I'm getting off to the edge. Yeah, it's not gonna be this soon. Magnitude of J hat. K hat, what angle does J make with K? 90, so 90. So magnitude of unit vector 1 times 1 times 1. Okay, crazy. So now if I didn't draw this, this is Z, Y. Okay. So J hat goes in what direction?
Y.
Y, so this is Y. Then we have K hat like that. So what is K, what is J cross K?
Arrow coming out the board.
J crossed into K is coming out. Right? So if you were to have your J here, and J here, this guy here is J cross K. So it's coming out of the board, has a length of 1, that's often called I have. That makes sense? So there's a dumb way to remember all these. Okay, so. Easy. That gives the result of crossing for crossing. Is the following. Okay. So you put I, J, and K in a circle like this, and you have to go this way. And then I have little arrows like this. And now this is how this works. If I do I cross J, what do you think it's going to equal? K. If I do J cross K, what is it going to equal? I. If I do K cross I, what is it going to equal? J. If I do J cross I, go the opposite direction, that would be minus K. I cross K,
Negative J.
minus J. K cross J, minus I.
That's handy.
That's actually the easiest way to do it. Okay. That makes sense? Okay. So tell me now what my buddy here is. Using our little,
Minus K.
does everyone agree? So we have J cross K, that has to be minus, I'm sorry, J cross I, that has to be minus K. So if we put this all together, what does this give us? A cross B equals, we get 0 from this guy. This guy gives us a minus and a minus, make a plus, 2 and 4 make 8. So this is 8 J hat. This guy here is 3 and 3, 9, but with a minus sign. So this is minus 9 K hat. And this guy here is going to be minus 12 I hat. Okay, normally I won't leave it like that because that looks kind of stupid. Normally it's always IJK, so I write this is I cross A cross B is minus 12 I hat plus 8 J hat. Minus 9. Now let's check. So how would you check that result? What had that better be? Yeah, as the check is this A cross B.
So if you take the dot and it'll.
Exactly. It must be perpendicular to both A and B. So if you take the dot product between two vectors that are perpendicular, what's the dot product between two vectors that are perpendicular?
0.
It's 0. So I'm going to give these a name. I'm going to give this a name. I'm going to call this C. So what we're going to do, we're going to check the C. If C dot A equals 0 and C dot B. That makes sense? Yeah. I need that. Oh, that's over there. Okay. So let's do this. Let's do a little review recall. Okay, what's another way to write this from first semester physics?
The dot product. It's
This is AX,
Yes.
BX,
Plus, yeah, B1.
AY, BY. Let's say ZBZ. Okay, and you do it just by putting in you put in AXI hat plus AYJ hat plus AZK hat, likewise for this, and you work it out. So let's work this out. What is the Ka term equal to?
That's how you need to do it on tests, is don't do C dot A, just do Ka. But that is minus 24 from the I.
And so what would it be? This is going to be what?
And then
It's
24.
going to be CXAX plus CYBAY plus CZAZ.
But the Z does matter, so just okay.
So let's do this. So CX is
Negative 24.
minus 12.
So
AX is CY is
8.
8. AY is
3.
3. AZ is minus 9. I'm sorry, CZ is minus 9, and then AZ
0.
0. So you can see this is 0. So that vector is perpendicular then to A. Yeah, let's do one more thing. Now let's do this guy. C dot B. So this is CXBX, this is CYBY, this is CZBZ. Okay. So CX is again our minus 12. BX is 3. CY is our friend 8. EY is
we would use the minus 9. It's K. Oh, no, no, sorry. Oh,
0,
Okay.
0.
0. Plus CZ is a minus 9. BZ is minus 4. 36 minus 36, Shazam 0. Okay. So the C we constructed is perpendicular to both A and B, which it must be. Does that make sense? Let me give you another way to do this. Okay. If this next way makes no sense, I don't know where everyone is mathematically. If this next way makes no sense, don't worry about it. You don't have to use it. Okay. So I'm going to draw something on the board. For some of you, it's going to seem incoherent. Don't worry about it. You can do it. You can do it this way here, and it'll always work. So another way to do this, it's actually the fastest way. So no, this is an aside. A very fast way. Calculate a cross product is to use a determinant. If that word means nothing, you don't worry about it. I'll show you how this goes. Let's get A cross B. This is the determinant. Okay, for those who have seen it, what's on the first line?
IJ.
IJK.
Is this IJK? Yeah, then here is going to be all the components of A. Okay. Then down here, all the components of B. Now there's a fast way to actually multiply these that actually works out a lot easier. There's a formal way to work this out. I'm not going to give it to you. I'm going to give you kind of a fast way that gives you the answer fast. This is going to seem incoherent. What you then do, you get to make noises with this too. Okay, they'll be the noises. Then do. That'll come with a plus sign. We're going to multiply those together. Then you're going to go. It's important to make that noise. Okay. That'll come in with a plus sign. Okay. Then it's going to be like that. And that'll come in with a plus sign. Crazy,
Whoa.
crazy, crazy, crazy. We're not done. Okay. Now what we're going to have. We're going to have. That'll come in with a minus sign. Then you're going to have. That'll come in with a minus sign. Then that'll come in with a minus sign.
This is the easy.
And that is the
Whoa.
fastest way to do this. Now, that comes across as like, what hell just?
Well, it
Okay.
makes more sense to do.
That's actually the
arrows.
fastest way to
big
do this.
Arrows aren't being known.
Okay, let me show you how this, well, I guess technically classes.
We have time.
Monday.
We'll do it on Monday. Okay, have a great weekend. Yep.
I want to ask you a question about
Yep.
this problem with
Yep.
Why is the force, why is the, well, the force and the prospect of this?
Well, we're gonna.
Yeah, okay, because I did the problem. As the point that it's talked about. It should be like.
Actually, I talked about support. When I talked about support, then you.
Well, I did the personal projection on B. That went forward, but it-
That's only gonna be total for the next. Thank you. Take care. You as well. Bye-bye.
Yeah, I did a thing.
Good,
I
thank you.
I'm so used to curveballs at this point. I'm so used to.
Oh, yeah. Studying